Hello, the book's name is Problems in General Physics by R.E. Irodov, and I'm going to solve question number 1.57 of this book. I found this problem to be a pretty interesting one and it took me an awful lot of time to solve this. Okay, so I'll be solving this question. A round cone with half angle alpha is equal to 30 degrees and the radius of the base capital R is equal to 5 centimeters rolls uniformly and without slipping over a horizontal plane as shown in figure 1.8. The cone apex is hinged at the point O, which is on the same level with the point C, the cone base center. The velocity of point C is v is equal to 10 centimeters per second. Find the moduli of A part, the vector of the angular velocity of the cone and the angle it forms with the vertical. In part B, and the last part is the vector of the angular acceleration of the cone. So first of all, let me draw this figure like this. And I'm assuming here that this thing is rotating like this, okay, in this direction, that is the anti-clockwise direction. And this is the point C over here. As you can see, this is point C, and the speed of point C is given in the question. Now suppose somebody is standing over here. Let me change the color of it. Suppose a person is standing over here and he is watching from this direction. What will he see? If he is looking at the cone from this direction, what will he see? So he will see something like this. See that there is a circle over here, okay, and this point is the point C. The radius of this part is given as 5 centimeters. So let me just call this distance is capital R, and capital R is equal to 5 centimeters, okay, and this is, suppose this is the base, okay. And when the person which I have made in red, when he is looking at the cone from that direction, he will just see this disc because the rest of the cone will be hidden behind the disc, right? Now suppose I need to calculate the velocity of this point. Now if you know your rolling motion, you would know that the velocity of this point, let's call it say point A. This point is, say this is point A. The velocity of point A needs to be equal to 0 because this is the condition for pure rolling motion, okay. And over here what I can do is, see, this point A will have two velocities. One velocity, suppose this is rolling like this, like suppose this disc, the part of the cone which is visible to the person is moving in this direction, and this point A will then have two velocities. It will have one velocity because of the rolling part and another velocity because, see, the velocity of point C is 10 centimeters per second. It is mentioned in the question that this velocity is 10 centimeters per second. So this point will also possess this velocity because it is also undergoing translatory motion. So this point will have two velocities. One velocity will be simply v, which is equal to 10 centimeters per second, 10 centimeters per second, and this another velocity over here will be actually, let's call it omega multiplied by r, and for convenience let me call this omega subscript 1, that is omega sub 1 multiplied by r. But as I said that the net velocity of this point needs to be 0 because it is a pure rolling motion. So this simply means that the value of small the value of small v should be equal to omega 1 multiplied by r, okay. So let's say this is my equation number 1, okay. And if you want to relate this to this image, see, this is capital R, and let's say that this line over here is, let's say this is small r, okay, and this angle over here, this will be alpha because the total angle that the cone is making with the vertex is with the with the point O is 2 alpha. So this angle would be half of that angle, which is simply alpha, right? Now let's see. V is equal to omega 1 into r. Yes, so angular velocity, both angular velocity and angular acceleration, both of them are vector quantities, and they both are axial vectors. So if I need to draw that, let's first take the first part. Suppose this is the cone over here. Okay, this is the cone, and this cone, as I said, it's moving. This part, the disc part of the cone is moving like this. This is the point C. Okay, and if it is revolving like this, then this omega 1 will be directed like this, because I'm using the right hand thumb rule. You curl your fingers of right hand in the direction of the rotation of this of this disc, and your thumb of right hand will point in the direction of the axial vector, that is omega 1. So this will be omega 1 over here. Okay, now let's deal with the other part. Now let's take the other part. But as it is mentioned in the question, this cone is actually also rolling down this plane, so it is also moving in somewhat this direction. Okay, now see the velocity of this point. Let's see that it is moving like this and like this. Okay, the velocity of this point is given in the question. It is 10 centimeters per second, right? And this rolling motion, because this cone is moving in the anti-clockwise direction about this point O, so therefore the axial vector for angular velocity, okay, this is the axial vector for angular velocity, which is due to this rolling motion. Okay, and one more thing, this angle is mentioned in the question. This angle is alpha. This point is moving with a velocity of 10 centimeters per second, and this distance is given in the question, that this distance, the radius of the base, is capital R. Let me call this distance to be small r. Okay, so these are different r's. That this one is small r, that one is capital R. And if I focus on this triangle, let me separate this triangle over here. It means you can see this triangle. This is the point O. This is the angle alpha. This length is capital R, and this length is small r. So as you can see in this triangle, tan alpha will be equal to perpendicular upon base, and perpendicular here is capital R and base is clearly small r, because the remaining side is the hypotenuse. So tan alpha is equal to capital R divided by small r. Okay, so, and yeah, one more thing, we need to find the angular velocity omega 2 about the point O. Now we know that the general formula is V is equal to omega R. V is equal to omega R, but here what will be omega and what will be R? These terms are important. V will remain V. This omega is, I am calling this as omega 2 in this case, and the distance of the point which is moving with the velocity V, this point and the point O, the distance between these 2 points is small r, right? So I can write it as omega 2 is equal to V divided by small r. But I know from this equation, this tan alpha equation over here, that if I refer to this equation, tan alpha is equal to capital R over small r, then small r will simply be equal to capital R over tan alpha. Okay, and then I can substitute that value over here. If I substitute this value of small r into this equation for omega 2, I will get omega 2 is equal to small v divided by small r, small v divided by small r. This is equal to r divided by tan alpha, r divided by tan alpha, and this will then become omega 2 will be equal to v over r multiplied by tan alpha. So this is the value for omega 2, and this omega 2 is directed in the upward direction, whereas this omega 1 was directed in the left hand side direction. Okay, but omega is a vector quantity, so and both these vectors are perpendicular to each other, so we can simply add the two vectors. So omega vector will be equal to omega 1 I cap plus omega 2 j cap, right? I mean, I'm assuming over here, let me draw the cone again. Here's the cone, suppose this is the cone, and suppose this is the y-axis, and this is the x-axis. Okay, y-axis, x-axis, and this cone is moving like this. Okay, and it is also rolling like this. The cone is doing a combination of these two motions. Now see, and yeah, one more thing. One thing is very important here, that this x-axis is not fixed. This x-axis is moving with the cone. The y-axis is fixed because in the direction of y-axis is fixed because the cone is moving in this direction, is moving like this. It's moving in the anti-clockwise direction. So omega 2 will always be directed towards the y-axis, the positive direction of y-axis. That is okay. But omega 1 is directed towards the x-axis, and because omega 1 is directed towards the x-axis, but because the cone is revolving, therefore this x-axis will also keep revolving because because the cone is revolving, therefore the x-axis will also revolve. However, our calculations won't be affected by that, at least not in this part A. So omega vector can be written as omega 1, which is equal to small v divided by r I cap plus small v tan alpha divided by capital R into j cap. Okay, so this is the value of omega vector. But in the question it said that we need to find the value of the modulus of this vector. Find the moduli of part A, the vector of the angular velocity of the cone and the angle it forms with the vertical. Okay, so let me first of all find modulus of this vector. Now once you know the x and y components, it's very easy to find the modulus. The modulus will simply be modulus of omega vector will be equal to the square root of x square plus y square, that is the square of x component plus the square of the y component. So this will become v square divided by r square plus v squared tan squared alpha divided by capital R square. Okay, so this is the value of modulus of omega, and this then can be written as v square over r square can be taken out to be as the common term, and there's a square root above, so this will simply become v over r, and this will be the square root of 1 plus tan squared alpha. But we know that tan squared alpha plus 1 is sec squared alpha, so this can be written as modulus of omega can be written as v divided by capital R, the square root of sec squared alpha. This will just become simply sec alpha. Okay, and we don't need to use the modulus sign over here because it's given in the question that alpha is only 30 degrees, that is alpha is lying in the first quadrant, and we know that all t ratios are positive in the first quadrant, so we don't need to add a modulus sign on sec alpha. So this is the value of modulus of omega vector, and this is the answer in terms of algebraic quantities. Now we can substitute our values and find the numerical answer. So modulus of omega vector is equal to v over r sec alpha. Modulus of omega vector is equal to v over r sec alpha. Sec alpha. Everything is correct. Now let us substitute the values. As I said, this will imply omega vector modulus of omega vector will be equal to v. V is 10 centimeters per second divided by capital R. Capital R is given as 5 centimeters, and the value of sec alpha can be 1 upon cos alpha. Sec alpha is 1 upon cos alpha. The value of alpha is 30 degrees, so this will be cos 30 degrees. Okay. Now see, we don't really need to change these quantities into their SI into SI units. Why? Because this centimeter will cancel out with this centimeter in the numerator. This centimeter in the numerator will cancel out with this centimeter. So changing into SI units is not really necessary. You will get the same answer. So omega vector, the modulus of omega vector can be written as 10 over 5, which is simply equal to 2, and the value of cos 30 is root 3 divided by 2. Okay, so this can be written as 2 multiplied by 2 divided by root 3, which is equal to 4 divided by root 3, and the unit will be, of course, radians per second. Okay, so this is the answer. This was the answer in algebraic form, and here this is the answer in the numerical form. Numeric form. Okay, 4 upon root 3 radians per second, and you can just solve this value. 4 upon root 3. I mean, I'm just making sure that my answer matches with that given at the end of the book. 4 divided by root 3. I'm using my calculator now. 4 divided by the square root of 3 is 2.309. We can take it as nearly equal to 2.3. Yeah, so this is approximately equal to 2.3 radians per second, and this matches with the answer which is given at the end of the book. So this is the final answer. Okay. So we need to find the angle that this omega vector is making with the vertical. Okay, so this will be let's say that the net omega is in this direction. This is omega vector, and we need to find this angle. Okay, let's say this angle is x degrees. Now it's clear from this figure, it should be clear from this figure, I hope, that the value of tan x will be equal to perpendicular upon base. So that will be equal to the perpendicular here will be omega 1, because see, if this is omega 1, so is this, this is also omega 1, and then this is omega 2. So so we need to find the value perpendicular upon base. The perpendicular will be omega 1, and we have to divide this by omega 2. So tan x is equal to omega 1 divided by omega 2. Tan x is equal to omega 1 divided by omega 2, and from here we know that omega 1 is equal to v over r. So v over r whole divided by omega 2. Omega 2 is equal to v tan alpha divided by r. V tan alpha divided by r. Okay, so this can be written as v divided by r divided by this much multiplied by r divided by v tan alpha. So these two r's will cancel out, this v will cancel out with this v, So we are left with 1 upon tan alpha, which is simply equal to cot alpha. Okay, so the value of tan x, this whole is equal to 1 divided by tan alpha. So tan x is equal to 1 upon tan alpha, but the value of alpha is 30 degrees, so this will be equal to 1 upon tan of 30 degrees. So this can be written as 1 divided by 1 over root 3, which is simply equal to the square root of 3, and tan x is equal to root 3. So this will of course imply that x is equal to 60 degrees. This is the answer. Okay, now let's deal with the second part. The B part, the vector of the angular acceleration of the cone. Now see, this is slightly more difficult. Why? Because see, first of all, okay, let me call this equation as, let me say that this is equation number 1. Okay, omega vector is equal to this. Okay. Now see, we need to find the angular acceleration vector. So the angle, let's call that beta vector. So beta, I'm just using the same notation which Irodov has used. He's calling it as beta vector. So let me also use the same notation. Beta vector is defined as, of course, d omega vector by dt. So this can be written as d by dt of omega vector, but omega vector is v over r I cap plus v tan alpha over r and j cap. Okay. Now so this problem this problem might appear to be an easy one, but actually there is a trick. There's a trick which is to be used here. See, I mean, because some people will think now we just have to differentiate this equation and we'll get the answer. Yes, but the differentiation part is difficult. Why? Because see, I told you here that the x-axis is moving; it is not stationary, but the y-axis is stationary, which means that if the x-axis is moving continuously, then I cap vector is a variable and it is not a constant. This means that this I cap is actually a variable, and this will get differentiated, because otherwise in ordinary differentiation what we just do is we assume that I cap, j cap and k cap, they all are constants, and we differentiate the remaining parts. But here I cap is a variable because its direction is continuously changing, therefore it will also get differentiated. So let me write it this like this: beta vector is equal to d by dt of v over r into I cap. This is the first part of this expression. So v and r are constants, they can be taken out of the differentiation sign, but d I cap by dt, this will get differentiated. And the second part is easy, because in the second part the second part of the expression is v tan alpha divided by r multiplied by j cap, and here everything is a constant, because I said here the y-axis is stationary, y-axis is not moving. So if y-axis is not moving, then it means that j cap, the direction of omega 2 vector, is a constant. Okay, so di cap by dt beta is, so yeah, the second term, all terms in this expression, let me highlight this for you. All terms over here, v alpha capital R and j cap. All of these are constants. Because all of these are constants, so when you apply d by dt to this, you will simply get a 0. Okay, so the value of beta vector is equal to v divided by r multiplied by di cap by dt. So if I know di cap by dt, I'll know beta vector. Okay, now let's see. Suppose, let me draw the two axes once again. Suppose this is the x-axis, which is rotating, and here's the y-axis, which is fixed, and this x-axis is rotating. Okay, now suppose see, this will be the direction of I cap. Okay, and because I have to draw one more I cap, so let's call this I cap 1, and after some time, let's say this I cap has moved over here, and let's say that this is I cap 2. Okay, and suppose this has moved from here to here. Now it should be clear that this vector, this arrow over here, this will be equal to di cap. Why? Because you just use the triangle law of vector addition. See, if I take this I cap 1 plus di cap, it is clear from this triangle over here, that I1 cap plus di cap will be equal to I2 cap, right? So di cap will be equal to I2 cap minus I1 cap. So of course, the final value of I cap vector minus initial value of I cap vector. So this is of course di cap, and di cap, I mean, this is how a differential is defined, final value minus initial value. So it's okay to say that this is di cap. Now suppose this angle over here, suppose this angle is d theta. See, because we are dealing with small changes in I, therefore the angle will also be small. So because there is a small change in I, that is di cap, so the angle will also be just a small angle. So that's why I'm calling it d theta. Now see, there's a formula that angle is equal to arc over radius. Angle is equal to arc divided by the radius. Now see, this angle, this will imply that angle is d theta. This will be equal to the arc. Now because we are just dealing with differential elements, we are dealing with very small things, so approximately this arc can be taken as equal to di cap modulus of di cap. Okay, this is an approximation. So d theta will be equal to the modulus of di cap divided by the radius. Now radius means the length of this I1 cap or I2 cap vectors, but as we know that I cap is a unit vector, so its length will be 1, so the denominator will simply be 1. So d theta is equal to modulus of di cap divided by 1, or d theta is simply equal to modulus of di cap. D theta is simply equal to modulus of di cap. Okay, now what I can do is I can divide both sides by dt. Divide this side by dt, divide this side by dt again. Now this will imply d theta by dt. Now you need to make sure that, see, this I cap, this I1 cap or I1 cap changed into I2 cap, but it moved around the point O, and this angle I have taken as d theta. So which part of the vector is which part of omega vector is responsible for this motion? Now if you think about it, you will find V over R tan alpha. This omega 2 will be responsible for it, and because omega 2 is responsible for it, so I can write this d theta by dt as omega 2 this will be equal to the modulus of di cap divided by dt. Okay, now let's see. Yeah, but the value of a beta vector, you see from this equation, the value of beta vector, I mean, look over here, I'm highlighting with green. I'm trying to use this equation now. See, over here I can say that this is beta vector, but we are not required to find the value of beta vector. We are required to find the modulus of beta vector. So the modulus of beta vector will be equal to v over r multiplied by di cap by dt. Don't worry about the color change, that is sort of automatic, I cannot control it. So the modulus of beta vector will be equal to v over r into modulus of di cap by dt. Modulus of beta vector, modulus of beta vector is equal to v over r multiplied by di cap by dt, and the modulus should be here also. Okay, v over r di cap by dt. Now this can be written as then yeah, but di cap by dt is equal to d theta by dt, and that d theta by dt is equal to omega 2. So this can be written as v over r multiplied by omega 2. Okay, and the value of omega 2, we know the value of omega 2 is v tan alpha over capital R. V tan alpha over capital R. So I can write this as v over r multiplied by omega 2, which is equal to v divided by capital R multiplied by v divided by capital R multiplied by tan alpha. Okay, so the modulus of beta vector then becomes v square divided by capital R square multiplied by tan alpha. So this is the correct answer. This matches with the answer which is given at the end of the book. Now we can just substitute the values to find the numerical value. The numerical value of beta vector would be what? V was, I believe, 10 centimeters per second. So the square of 10 divided by capital R. Capital R is given as 5 centimeters. So the square of 5 multiplied by tan alpha. Tan alpha is tan 30 degrees. Okay, so again you don't need to change the units because the centimeters will cancel out, so you don't really need to change centimeter into meters. You'll get the correct answer this way. This can be written as 100 divided by 25 multiplied by 1 over root 3. So this will become 4 over root 3, which will just become the same answer which we got earlier numerically, but the units will be different. Yeah, 2.3. 4 over root 3 is 2.3. So 4 over root 3 is equal to 2.3 radians per second squared. So this is the final answer. If you like this video, please give it a thumbs up. And if you want to see more such content, then please subscribe to the channel. Thank you for watching.